In this video, I want to show you how we derive specific results, extract fundamental relations, and get to the next level in our physics problem solving. So let's take a look at an example. Imagine we launched a ball straight up with some speed v. Of course, it would go up and then eventually it would reach what's called the maximum height, the highest point it will go vertically before it comes back down. Now, what if we launched it at twice the initial speed? Maybe we had a stronger cannon or we threw it up for whatever reason with twice the initial speed. Well, a great question you might be thinking as a curious person is, well, would it go up like twice as high or something? Or maybe not quite twice as high, or maybe more than twice as high? Like how much higher would it go compared to when we first threw it up? So notice what we're doing here. We have kind of set like this base case of some phenomenon when we shoot it up at speed v. And then we're trying to compare a new scenario to that kind of base case. And in this case, what would happen if we fired it at twice the speed? So I'd like you to pause the video and think about this and see if you can figure it out. And I want you to try as hard as you can to not plug in any numbers whatsoever into any equations. I know that might be kind of hard to do. You might be tempted to plug in some kind of dummy numbers, if you will, make up some values, and then just work it out. I'm trying to get you away from that lower level of working with the equations of motion and take you to the next level where we do things in variables and then we extract relationships and then we see how those relationships behave using what's called proportional reasoning. So pause the video and see if you can figure out exactly by what factor this max height would change by if we doubled the initial speed, and then we'll take a look together. All right, so let's take a look. Now the first step here is to identify some things that are totally true about this system. This is called identifying our first principles. That's a phrase that is often used to talk about the fundamental laws of nature and concepts that apply to a particular scenario. So for example, in this case, we're dealing with free fall motion where we have constant acceleration and we know that value, and the magnitude of that acceleration is about 10 meters per second squared here, close to the surface of the Earth. So we've identified a fundamental concept, right? And then usually once you've done that, there tends to be in physics an associated an equation, and not always because you might just be working through a conceptual problem or something, but if you're trying to get to kind of like a mathematical result, there tends to be an equation that's related to that concept and to the system in general. Now what we need to do is apply these first principles to the specific scenario. And in doing so, we'll be using our own variables that we create and our own kind of custom subscripts to communicate clearly and specifically. Since we're not plugging in any numbers, we want to be able to plug in and make up variables that make sense to communicate the phenomenon. So let's kind of do that together. And this is, you kind of get used to this as time goes by. There's kind of an art to picking the variable you want to use and the subscript that communicates what you're trying to communicate clearly. And what you'll see here is pretty standard for like a one-dimensional motion type of problem. So we'll come in and first we'll realize that our initial position is 0 meters. And up here at the top, at the maximum height, we realize that we don't have any velocity. That's a really important concept. That's not said to you explicitly. That's where the critical thinking comes in here. Also, we could write up here at the maximum height something to do with our final position. And you might say, can we just keep it like this? Y sub f for the final position? Yeah, I guess you could, but that doesn't really communicate very well that this is the maximum height, and we were trying to do that. So instead, we're going to turn this into something that communicates a lot better, and we'll do y max. All right, cool. So let's write out our equation. Oh, and I'm sorry, actually, before writing out the equation, we also know one more thing. We know that our acceleration value is equal to minus 10 meters per second squared, assuming we have the classic coordinate system where up is plus and down is minus, like this. But again, we don't want to use a number here, so we're going to use the gravitational field strength, lowercase g, as a placeholder for the gravitational field strength. And since our coordinate system choice over here on the left has up as positive and down as minus, we're going to need to have a minus sign out in front there. And I won't go into, how you conceptually know that. We've done that before in previous videos, but that should be something I hope you're familiar with, why there's a minus sign there. All right, now moving forwards, let's plug everything into our formula. All right, so let's go ahead and do it. Let's try to whittle this equation down. And we'll start by crossing things out that are 0. So the initial position is 0, so we can cross that out. Now over here, we also know that the velocity up at the top, the maximum height, is also 0. So you might be tempted to cross this out, but remember what this is. This is the initial velocity, right? That's whatever this value is, and we don't know what it is. It's just going to be represented by VI in our equation. So we skip over that, and then we would come over here. Oops, wrong color. And we would plug in a minus g for our acceleration, t squared. Still got to keep this. And then we would turn this into y max. Now, can you see a problem? I've kind of done this on purpose. You should be seeing a problem. There's really nowhere to go further to get to a simple relationship between the maximum height and the initial velocity because we got the variable t in there. So how much time does it take to get up to the maximum height? We'd have to know that. So I purposefully have done this to show you that we've run into a dead end here. We chose an equation from our equations of motion that won't get us anywhere unless we use another equation in conjunction with it, which you could do. But I'm going to show you an easier way. So what we should have done at the start of this, when we wrote down our first principles, is we should have written down all 3 equations of motion and just kind of looked over all 3 of them before we went on this journey to pick out one of them. And that's worth your time usually when you're doing these problems, is just take a step back for a second and look at everything from a 10,000 foot level before you drill down into some more specifics. All right, so what I've done now is I've written down the correct equation that we'll use, the third equation of motion, and then we'll solve it. So again, crossing things out that are 0. Well, we look here and we say, okay, final velocity, where's our final point? Well, we decided to choose it, and we chose it over here. I didn't actually write these out, which I should have done earlier. That's okay. But I typically like to write lowercase I and f to deliberately show my initial and final points on my drawing. And now we can see that our final velocity over there is 0, so we'll cancel that out. Great. Now our initial velocity, it's moving upwards, so it's positive, and I tend to like to use v sub I. That communicates that it was the initial velocity that this object was shot up at. So we'll leave that as vi squared, which is great. And then we'll come in and plug in, so we get 0 is equal to the initial velocity squared. Plus 2, let's plug in our minus g. And then here, got to be a little bit careful, got to expand out delta y, that's displacement. And so that would be y final minus y initial. We see another place where we can cross something out. Y initial was 0, so that goes away. And then with our custom subscripting over here, our y final is better communicated by using the language y max, and so we'll plug that in. And so let's just keep writing this out all the way. So 0 is equal to initial velocity squared minus 2g times y max. Looking good. You could probably finish it here in your head, hopefully, and you can see now that our maximum height is going to equal the initial velocity squared divided by 2g, and we'll put a box around this. Hopefully you're able to get that on your own, but if not, don't worry. You'll build that skill up over time as you work abstractly with these symbols and subscripts. But again, notice how good the communication here is now on the page. We're explaining exactly what this is. This is the maximum height. And it looks like it's depending on 2 things. We see an initial velocity term, and then we see the gravitational field strength here in the denominator. So there's a lot to unpack actually from this simple looking formula. Of course, I could give you like 10 problems in a row where you could plug in just random numbers and solve it a million times, but that really wouldn't teach you what this is really saying. There's like a story here, right? So let's try to kind of unfold that. And I'd like you to pause the video and extract the 2 relationships that you're seeing here. So go ahead and try that. I'll write it like this. There's 2 things that you're going to see. Y is proportional to something, and then it's proportional to something else. go ahead, pause the video, and extract the two relationships out of this specific equation. All right, so I've done it here for you, and we have our specific equation, and we can see that y max is proportional to the square of our initial velocity. That's called the squared relation, and it behaves mathematically in certain ways. We'll take a look at that in a second. And then likewise, over here we can see that y max is inversely related to the gravitational field strength. So as long as we keep one of these things constant, for example, let's say we're always on the surface of the Earth, where g is negative 10 meters per second squared, right? So this g here would always be a constant value. 2, of course, is always a constant. Well, then we could talk about varying the initial velocity and immediately understanding how the maximum height would be changing, as long as that field strength g was constant. So let's look at that first here, and I'll give you a question to think about. Or actually, sorry, you already have the question. It was the original question. So why don't you apply now what you've learned here in terms of the fact that y max is proportional to the square of the initial velocity, and see if you can answer our initial question, which again, I'll remind you, it was that the speed has been doubled, the initial velocity, we're doubling it, and we want to know what effect that has on the maximum height. So what is this number right there, using the proportional reasoning skills that we have seen before? Okay, pause the video and figure it out. All right, so all you have to do is look at the type of relationship. It's the squared relation. And we need to do that mathematical operation, squaring something, to the factor by which we change the variable. So if we've doubled the initial velocity, we need to square that factor. So 2 squared is 4. And so we can see that y max is going to go to 4 times whatever that original was. And notice I've kind of labeled this here. You don't have to do this, but just to remind you that y max, when we write that down right now, we're trying to communicate that is however high the ball went in our base case before any change took place, right? It could be a certain number of meters. We never specified it, but that is what y max represents. And so here, well, we can see 4 times whatever that maximum height was in our base case. That's now our new height. And of course, we could write a variable for that if we wanted to. We could write like, I could come over here, I'll do that, and we'll write, I don't know, y new max is equal to 4 times y base case max. Probably not the best to kind of do this. This gets a little cumbersome with these very specific subscripts I'm trying to explain this with. So you probably wouldn't do that. But I wanted to point that out because students often can get really confused sometimes with what all these subscripts are for and what they really mean and how to interpret them. Okay, so that's what's going on. Now let's look at this other relationship that we found as well, how the maximum height here depends upon the gravitational field strength. And if we just isolate in on that relationship, well, we need to keep our initial velocities constant. So I've done that here. We can see that we're on the surface of the Earth and shooting it up at some initial velocity, and then we're on the surface of the Moon, and we're also shooting it up with the same initial velocity. And now the question, of course, would be, compare the maximum heights. Well, we need more information, right? You're thinking to yourself, I need to know something about how gravity changes when I go to the moon. And so I'll tell you, I'll give you that information right here. The gravitational field strength, and let's see, let's do this in blue. The gravitational field strength on the moon, we'll call that G moon, is approximately equal to 1/6 of the gravitational field strength at the Earth. And this is the surface for both things, by the way. Okay, so G moon is 1/6 of G Earth. So now my question to you is this. predict by what factor will the ball launched on the moon change by in terms of its maximum height. All right, go ahead, pause the video and see if you can figure out by what factor that change happens. Go ahead. All right, let's take a look. And we do this exact same logic. We identify the relationship. This is the inverse relationship. What is the operation to do that? Well, it's 1 divided by something, or I have also put raised to the minus 1 power. You can do both. I'll just leave it like this for now, but in terms of this line down here at the bottom, and then I'll rewrite this as I work it out. So what that means is 1 divided by 1/6. Of course, that turns into 6. All right, so then we would write out the answer that the maximum height would turn into 6 times as much as before. A pretty interesting result. So if you were to go onto the surface of the moon and shoot this ball straight up at exactly the same speed that you launched it the surface of the Earth, ignoring air resistance, then we'd find approximately this ball going up about 6 times as high. And this would also work if you jumped. So if you were on the moon and you decided to jump up on the moon versus jumping up here on Earth, of course you'd have an initial velocity upon your launch off the surface of the respective planetary bodies, and you'd go up 6 times higher on the moon than you would here on Earth, ignoring air resistance. All right, let's take you up to kind of the highest level here for where I want you to be able to think. And we're going to change 2 things at once. So again, we have our specific result here, all in variables, that helps us understand this relationship between Ymax and then these other 2 parameters that Ymax depends upon. And then what if we kind of modified our question about the Earth and the moon, and we said, look, we know that when we go to the moon and we fire that object straight up, it's going to go 6 times high, or 6 times higher than on Earth, because gravity is weaker. But what if we don't want that to happen? What if we want the object on the moon to go to the exact same height, and I'm shown that here, that it goes at on the Earth? Well, we can't change gravity, right? We can't hit a button to lower the, or to increase the gravitational field strength on the moon. But we can manipulate the velocity that we shoot it up at. Okay, so this is where we're now going to be changing 2 things at once. Not only as we go from the Earth to the moon are we changing the gravitational field strength down here in the denominator, but we're also going to manipulate the initial velocity up here in the numerator. And we want to make it such that the 2 effects balance out and we end up having no change at all in our maximum height. So why don't I let you pause the video first to see if you can work this out using proportional reasoning. What would you do here? Okay, and then I'll show you how you would do it. Go ahead, pause it, and to be real specific, the question is, by what factor should we change the initial velocity such that the 2 objects, both on the Earth and the moon, reach identical maximum heights? Go ahead, pause the video, and figure it out. All right, so let's take a look. And first, I'll show you kind of what's happening here in terms of the relationship. We extracted out from the specific equation that Ymax is proportional to these 2 things at the same time, vi squared over g, because both can now change, right? 2, of course, is a constant, so we can ignore that. But if both of these things are changing, then we'd have to write both of them down in our relationship. So notice that you don't have to just extract one variable for a relationship. You can extract multiple variables if multiple things are being allowed to change in your particular analysis when you're analyzing something. And so I've written down here that the field strength is going to go to 1/6 of the original field strength because we're going to the moon. And now we need to figure out by what factor this changes over here. And in doing so, we'll see that the maximum height, well, it doesn't change. It just goes to 1 times whatever its initial value is. This is kind of redundant here to write this out. All right, so we got to figure out what goes in parentheses. And you might be tempted to solve for like v initial. Just real quick, you might have done something like this, which is fine, but I'll make a note about it. So this would be v initial squared over 2g. And you might have said, okay, well, v initial therefore would be 2g y max take a square root, something like that, and then done proportional reasoning there, because you know this is going to be the same, and then you can work it out, right? That's one way to do it, and you get the right answer. But I like to do it in this other way because the maximum height depends upon these two properties over here. It's not the other way around. So the initial velocity doesn't depend upon the maximum height that this thing goes up to. That doesn't really make sense with like cause and effect. So we tend to like to keep that written down in the way where we have the things over here on the right, things that we can change, and then those cause these things over here on the left to happen in the world. Okay. So with that in mind, I think the easiest way to do this is just to leave everything up like we have it over here. So we've got vi squared divided by g. And then we want to balance this thing out. So whatever we do to the top, we need to do to the bottom, or vice versa. So let's do that. So on the bottom, what we're doing is we're changing g to 1/6 of what it is. So we'll put the factor 1/6 like that. And then, well, we need to do that on the top as well. How can we produce the number 1/6 on the top? But you gotta be careful because you need to remember that we've got this operation where this thing is being squared on top, right? So pause the video and see if you can figure out what you'd actually have to plug in, and I'll give you a little bit of a hint here. Up here, obviously you're going to have to square something, okay? So go ahead and see if you can figure out what goes in parentheses. All right, so let's take a look. You can see that because of the squared relationship in the numerator here, we need to put our factor under a radical, because when you square the radical, then you will remove it. And so you square the square root of 1/6 and you get 1/6. And then you need to, and then that'll cancel out with the 1/6 on the bottom, which came from the change in the gravitational field strength when we went from the Earth to the Moon. 1 over the square root of 6 is about 0.41 when I worked out the math and did a little bit of rounding. So we can see that we would need to launch the ball at about 41% of the initial velocity that you launched it at in Earth, or that you launched it at on Earth, to get it to go to the same maximum height on the Moon. And this is incredible. Notice we didn't have to get bogged down in any like little calculations of meters per second squared and all of that with the specific formula. We were able to extract this from the relationship because we knew how the maximum height depended upon initial launch velocity and the gravitational field strength. All right, so I want to make sure you really got this. We're going to do another example, and I want you to figure out if we double the initial velocity and then quadruple the gravitational field strength, what happens to the maximum height? By what factor does it change by, or is it unchanged? Pause the video and figure it out. All right, so the question is, well, what's the operation that we have to do? Well, there's two operations. There's a squaring in the numerator, and then there's dividing by another factor. So the way I tend to like to write that is I'll write my relationship as you can see here, and then I'll put a colon, and then I'll go ahead and do the factors with the operations. So the factor for the speed change is 2. It's a doubling in speeds, but we need to square that because of that factor, and then, or because of this 2 here, and then we have to divide by the other factor, which is a 4. So it turns this process into a pretty simple type of operation mathematically. And in this case, we get 2 squared, which is 4. 4 over 4, well, that's 1. Interesting. So if we want to, if we go back to our original problem all the way at the beginning of the video, and we doubled our initial velocity, we realized that the object went up 4 times as high because of the squared relationship. So we double the initial velocity, and we go up 4 times as high. But now, if we come along and also manipulate the gravitational field strength, and we quadruple the gravitational field strength, interestingly, if we could, right, we could kind of neutralize that effect of shooting it up twice as fast, and they would still go up to the same maximum height. Or perhaps we could, instead of quadrupling the field strength, maybe we could only double it. And we come along, we work out the math again. We square our doubling in speed, and we only can divide by 2. So what does that happen? Well, now we get 4 over 2, and we get 2. So 2 times the maximum height. And I hope you can now see how you are able to mentally play around with these factors and then figure out how the system will respond to changes. Remember, that's what we're trying to do here. We're trying to take a step back from plugging and chugging into equations and really understanding deeply what the system is all about, how changing one parameter will affect another, or how changing multiple parameters at the same time will affect another important parameter in our problem. So therefore, you could imagine if you had like a special box of sorts, and maybe it had, I don't know, 2 knobs on it or something, like dials on a radio, dial 1, dial 2, and these things could be turned to certain values like this, turned back and forth. And this was a dial for initial velocity, and this was a dial for gravitational field strength. So you turn those things, and then that's going to change something else about the world, and it's going to cause this number out in front of maximum height to change by some factor um, relative to some initial like base case when the knobs are like, I don't know, all the way to the left or something. And that's pretty cool. And so you can start to imagine how nature can become much more complicated in particular systems when we have a lot of things that affect other things. So in this case, it's pretty easy. You only have 2 things affecting maximum height when we shoot something up straight up in a gravitational field. But there could be other systems with like 3 variables, 4, 10 variables, all affecting that final variable that you're interested in. All right, so that wraps it up here. And what we've done is we've tried to get to this next level in our reasoning ability, this more abstract reasoning ability where we're getting away from plugging and chugging, and we're learning more about these systems through variables and constructing specific equations, extracting relationships, and then using proportional reasoning to understand how systems respond to change. Fundamental skills here when we're first learning physics. All right, take care, and we'll see you next time.